Okay. Hello, everyone. Thank you for joining the June Space Cafe Tokyo. And since we have, usually this is, this Space Cafe Tokyo is done at a very cozy British pub in Tokyo. But because we can't do any physical events right now due to pandemic, we have been doing this online since April. And because of that, actually, I see we notice people from outside Japan joining. And so the Space Cafe started a couple of years ago. And right now we have a small team doing it, and we do monthly public lectures in astronomy and space sciences, either by researchers who are based in Japan or those who are visiting. But now we have since we are doing it online, we have the opportunity to bring in people outside. So this week we have Dr. Inga Kamp, who's an astronomer. She studied physics in Germany and then did a postdoc in the Leiden Observatory in the Netherlands. And then also at the Space Telescope Science Institute in Baltimore. And now Inga is based at the Astronomical Institute in University of Groningen. Inga is researching into birthplaces of new planetary systems and sort of balance between chemistry and astrophysics. So it's a quite interesting combination. And you can imagine looking at the title, Mixing Drinks in Space, definitely you need some chemistry. And so apart from doing astronomy, I heard from Inga that she's also a chair of a book club and also does gardening. And these two are definitely quite well fitted for quarantine times. And I also want to introduce our team. So we have Ken. Ken, do you want to say hi?
Hey, everyone.
Yeah. And then Mayuko.
Hi, everyone. Thank you for joining.
And then Ayako, who organized the Japanese version of Space Cafe, and Michelle, who joins us helping with organizing and also photographing when we have the physical event. And this is basically us. And even though we are doing it online, I kind of want to give a shout out to the British pub that we usually host this event, which is called Good Heavens British Pub. If you are in Tokyo and if you ever come to Tokyo, please check it out. They have really good food and they have really fun events pretty much almost every week, including Tokyo Space Cafe and Perfect Liars Club and some book clubs and poetry reading and humanities. So many cool things. Right. And before we start, I want to remind everyone everyone who's on Zoom to mute your mic. And if you have questions, you can ask on the chat, both on Zoom and on YouTube, and our team will pick them up at the end, and Inga will answer these. Right. So I want to welcome Inga. Thank you so much for doing this. Yeah, floor is yours. You can bring your screen. Let me unshare mine.
Yep.
Right. Now you should be able to share your screen, Inga.
Yes. So. I hope you can all see the presentation now.
Yeah.
So first of all, thank you very much for inviting me and having me in Tokyo, even though it is a virtual experience, but I always enjoyed being there, and it's a great city to live. So what I would like to talk today about is mixing drinks in space. So it is a little bit of astrochemistry, and it takes you through different parts of our own galaxy to show you a little bit what kind of molecules we encounter there and actually what their relevance is for the drinks that we are taking. I mean, maybe you tonight later, but I still have a working day in front of me. So the first thing is, of course, space is vast, it's huge. And one of the questions you have is, how can we find something as tiny as a small molecule in this vast space? And so let me see, how can I go further? Okay. So how do we actually find molecules in space? Well, we use something that's very unique to molecules. We use their fingerprints. And one of the most important things is molecules are built out of different atoms. And because they have different bindings, different angles of bindings, they can actually move around. And so they can rotate, they can vibrate. And all these kind of rotations and vibrations leave their unique fingerprint in the light that we receive from different parts of space. So for example, what you see in the upper part is a water molecule where you have the oxygen, which is the red ball, and then the two hydrogen, the white balls. And you see that both you can change the length, the distance between the oxygen and the hydrogen, but you can also just change the angle of the molecule. And so these are really unique fingerprints, and each molecule does it in its own way. And so by looking at the light from different regions of space, we can actually figure out what kind of molecules are in those regions. And so the first quiz question I would like to ask to you is, if Mayuko can bring up the first quiz.
Yes, wait a moment.
Yes. Do you actually know which of these molecules that you see in the list has not been found in space to date? Glycine, adenine, glycolaldehyde, or hydrogen cyanide? So if you are on Zoom, you can actually actively vote in this poll. If you are on YouTube, you will be communicated the answer through the chat. So I can see that only half the people voted on Zoom. So maybe give it another second or so if you haven't made up your mind yet. Of course, it's not allowed to Google this live. That's not fair. Okay, I think we have about 80% of the people in, so I think it's fairly representative. So what I can see is that most people actually got it right. It's adenine that hasn't been found in space yet. All the other ones, including glycine, have actually been found. Most of them actually confirmed in space by multiple observations. Okay, so let me close this. So how do we actually go about to collect the light that we hope to receive from these various molecules? We have very big facilities on the ground, and you see a couple of examples here. So for example, when we go to very, very long wavelengths, radio wavelengths, we have the Green Bank telescope in the US. Then we also have the IRAM telescope in France and Plateau de Bure, which is on Pico Veleta. But recently we have a very great machinery for astrochemistry for detecting molecules, and that is Alma on the Chatnandor Plateau in Chile. And it's 66 radio antennas that really collect a lot of photons for us. And so even finding trace amounts of molecules in space has become much more easy with the advent of this big telescope. And another possibility we have, because certain molecules emit in a wavelength range where we cannot look through the Earth's atmosphere, is to use space telescopes. And we have had two beautiful space missions that operated at infrared wavelengths. So that's just a little bit beyond the optical light that our eyes are sensitive to. So you see in the upper left this diagram of the transparency of the Earth's atmosphere, and the rainbow colors is the light that we see with our own eyes. And you can see that as soon as we go a little bit beyond that into the regime of infrared wavelengths, the Earth's atmosphere becomes totally non-transparent. And so any molecule actually emitting its fingerprint in that region would not be visible to us with ground-based telescopes. And that's why we have built infrared telescopes such as the Spitzer Space Telescope and also the Herschel satellite. Those are the NASA and the ESA mission that have flown recently. And we use those satellites to collect photons from different regions in the universe, actually, mostly from the Milky Way. And maybe we can start quiz number 2, because we are talking now about our own galaxy. And I would really like to know from you, how large do you think is our Milky Way? Is it 100,000 light years across? Is it 10,000 light years across, or 1,000 light years? So 1 light year is the distance that light can travel within the time of 1 year. We know that the speed of light is actually limited, and we measure therefore the distance in how long it takes for the light to bridge a certain distance. So I want to know whether you understand really how vast the space is that we have at our disposal to search for molecules. And I see that about 70% of the people answered, 80% now. Well, okay, let's take this as a result. I think most of you underestimate how vast space is. So our Milky Way has a diameter of even more than 100,000 light years across. So our Milky Way is really huge. And the interesting thing is that we can really go into different parts of space and see what kind of molecules we encounter there. And one of the spaces, oops, the poll came up again. One of the spaces I would like to take you to is actually the galactic center. And so you see our Milky Way is actually a spiral galaxy, like many in the universe. And in the center, we have a massive black hole, but the center is also very rich in forming new stars. And so just below in the lower right corner, you actually see an image of the center of our own Milky Way. And you see Sagittarius A star, which is very close to that black hole on the very right. But you also see more to the left a region called Sagittarius B2, which is a giant molecular cloud. And it's a place where a lot of massive stars are actually forming. And it is one of the most richest regions in space in terms of finding complex molecules. And let me go and zoom in a little bit, because we have Alma now. Alma not only has a lot of collecting area to find all those very rare complex molecules, it also has, because of its 66 antennas being spread out widely, it has a huge angular resolution. And so instead of seeing, that region as a little blob in the previous image from the Herschel space satellite, we can zoom in with Alma into a region which contains a couple of stars only. So you see here an image taken at 242 gigahertz frequency, and the scale, the little white scale that you see, is 0.1 parsec. So that's like 10,000 astronomical units. And so we are looking here at a site where a couple of massive stars are forming. And this is a region where people have found very complex organic molecules. And I just list a couple here: acetic acid, glycolaldehyde, acetamide, aminoacetonitrile, ethyl formate, and so on. And it's especially interesting because it will be the first region where we can actually start thinking about how these molecules taste and possibly smell. So for example, the ethyl formate that you see here actually carries the smell of rum and also the flavor of raspberries. And this is very interesting because usually we think of space as being very vast, certainly not very conducive to life as such, because it's a vacuum. I mean, we can't breathe there. We don't have oxygen to breathe. There's no atmosphere. But still, we find very interesting molecules that we also find, say, in drinks on the Earth. So then there's another region I would like to take you to. So this was a region where massive stars are forming, but we also have regions where stars like our sun are forming. And you see here again another image from the Herschel Space Telescope in the infrared. wavelength regime, and it's a star forming region where a lot of stars like our sun are forming. And so I would like to take you into one of those regions, which is the Offerors region. And what we find there is, for example, ethanol. This is an alcohol that we definitely need if we want to make drinks in space. And you see on the top, actually, the different, the fingerprint, so to say, all the different frequencies that are associated with ethanol. So that's a C2H5OH that you see up there. There's also methanol, as you see right next to it, CH3OH. And there are obviously a lot of other molecules as well. But the interesting thing is that by looking at the photons that we really get from ethanol itself, we can evaluate how much ethanol is in this region. And so we can start to think, how much do we need in order to fill a glass of beer, for example? So you really need to come through this entire star-forming region with the area of a soccer state in order to be able to collect the amount of alcohol that you find in one glass of beer. So our way of detecting these molecules in space is extremely sensitive. We can see tiny trace amounts of these molecules, and because space is so empty, we really need enormous volumes to collect a significant amount of these molecules. In that case, the amount that would make up a glass of beer. There's also another interesting region where new stars are forming, and that is the Orion Nebula. And what you see here is the spectrum that has been observed again with the Herschel Space Telescope and with the HiFi instrument in particular, which was an instrument that was built here in Groningen, among others, at the Space Research Institute of the Netherlands. And it took a spectrum of the entire region, which was very, very rich in molecules. So you see here, actually, on top of all those little fingerprints, the identification of the molecule that this corresponds to. And so I want to draw your attention to one particular molecule, which is water. Because it's true, I mean, a beer contains alcohol, it contains ethanol, but obviously, you know, it also contains a lot of water. And so this is a region where we do find a lot of water, but still you would need the area of a Dutch backyard, so like 100 square meter area, to pull through this entire region in order to collect the amount of water that we find in one glass of beer. So, okay, now we have water, we have ethanol. There are a couple of other interesting molecules, hydrogen cyanide, for example. It has the smell of almonds. So you can start thinking about a very nice glass of amaretto, for example, where you have a beautiful almond flavor in there. Also, what we find in this region is amino acids and sugar. All of them is also an essential ingredient. For example, you would wonder, but it's true. So beer, for example, contains amino acids as well. And obviously sugar is also very important to make the drink much more tasteful. So unfortunately, one of the drawbacks is that these regions in space do not have the right mixture to yield a decent drink. No, because even if I take a Dutch backyard or a soccer state, there's not a single size that will bring me the right mixture that I need for a good drink in space. So I think in principle, there's no risk to have drunken astronauts. But one thing to keep in mind, the Russians always do it differently. So in the time that the Mir was still flying, there was alcohol allowed in space, especially cognac they had on the Mir for special occasions. So not really drunken astronauts, because you would get a little blob of cognac that you have to sip up with a straw or something. So it's not a big danger, but it's a fundamental difference in policy, I think, between the Russians and the US. Now, I would like to play with you quiz number 3, which is thinking about how empty space actually is. And so if we can look at the third question that I have prepared, it's about how many atoms we may find in 1 cubic centimeter of space. Is it 10 billion atoms? Is it 1 million? Or is it 100? So just think about it. The Earth's atmosphere actually, just for comparison, has 10 to the 19 atoms per cubic centimeter, just to give you something to compare to. So I see we have a lot of astronomers actually on Zoom. So people have a good idea about how empty space really is. About half the people voted now, and everybody got it correct so far. And I guess the other half will probably not vote anymore because they find the question too trivial, maybe. So let's stop the quiz. The correct answer is actually 100 atoms per cubic centimeter. And in fact, it is actually a little bit of a range. So you will encounter regions that are even a little bit less dense. So usually we say it's about 1 to 10,000 hydrogen atoms per cubic centimeter. And it really depends a bit, mostly on whether you are very far away from a molecular cloud when new stars are forming, or whether you are in the middle of such a molecular cloud, like I showed you a couple of examples of. So what does this really mean for chemistry in space? Well, in the Earth's atmosphere, if we have such a high density of atoms, actually, we know that molecules collide every 0.2 nanoseconds. So a nanosecond is 10 to the minus 9 seconds. So that's a tiny amount of time. On the other hand, if we look at space, which is really the best vacuum, we cannot build it even here on Earth to the same extent as we find it in space. The molecules will collide only every 1.5 years. And that is assuming this average hydrogen density of 100 atoms per cubic centimeter. So you can see that the time scale on which atoms can meet and form molecules is extremely long compared to the Earth's atmosphere. In the Earth's atmosphere, this happens on a nanosecond time scale. In space, it takes years and sometimes even longer to form a certain new molecule. However, because space is so vast, we talked about the diameter of our own galaxy, and also because we have so much time. If we form new stars, it takes hundreds of thousands of years to form stars. The material is cycled in the galaxy on timescales of 10 to the 6, 10 to the 7 years, so 1 million to 10 million years we recycle material. So we have a huge amount of time and we have a huge amount of space at our disposal. And that makes the formation of molecules likely. And as I showed you, we do observe them regularly, and so they exist in space. And the interesting question is now, how are they actually forming in space? So I would like to tell you two little stories about this. One is about how we form water in space, because water is so interesting also for ourselves. I mean, we as human beings, we require water in order to live. And so how does water actually form in space? And it usually starts with the formation of molecular hydrogen. So you bring two hydrogen atoms together and you form an H2 molecule. And that's the starting point. And then it differs a little bit whether you are in extremely cold regions in space, whether it's more warm, like room temperature, 20 degrees Celsius, or whether you want to do it on the surface of a dust grain. What you see on the lower right-hand side is a tiny little silicate dust grain. Usually when we think about dust in space, it's very similar to sand on the beach. It's silicates, for example, but they do have very, very small sizes. So maybe at most 0.2, 0.5, half a micron in size at most. Usually they are much smaller than that. But on the surface of these cold dust grains, we can have also atoms sticking and molecules forming. And so if we look at the very cold regions and we want to form water in the gas phase, we really have to go through a whole suite of ions interacting with molecular hydrogen. So you see, we start with a positively charged oxygen. So we have basically kicked out an electron. We have our positively charged oxygen, and subsequently we add molecular hydrogen to it to build all the way up to H3O+, which then recombines with an electron and forms water. So that is the what we call cold chemistry way of forming water. If it's much warmer, we can actually form water through neutral chemistry. So we don't have to ionize our oxygen first. We start plain with neutral oxygen, and we just keep adding molecular hydrogen to it. And because the temperature is warmer, actually we have enough energy in those collisions to overcome any barriers in those reactions. And so that way we can form water as well. And then when we look at our very cold dust grains, we can actually form water also on the dust grain itself, because we can have like atomic oxygen sticking on that surface of the dust grain, and we can also have hydrogen sticking on it. And then those atoms find each other on the surface, and they can form water in that way as well. And so there are plenty of mechanisms in space how to make water, and it really depends then which region we are looking at to determine which way we're actually forming water there. But apart from water, I also told you that we have much more complex molecules in space. So for example, glycoaldehyde or some very simple amino acids. How do we actually think those are formed in space? And again, we turn to the surfaces of these dust grains, because when we have extremely cold conditions, we can actually build up ice mantles around those refractory dust grains. So the silicate itself is a very inert material. It just survives under a lot of conditions in the interstellar medium. But around it, if it's very cold, we will have a mantle of ice, which is usually consisting of water ice, but also carbon monoxide, carbon dioxide, and also methanol ice. And so in those ice mantles, we have a lot of molecules, especially also a lot of carbon-containing molecules at our disposal. And if we process those ices, if we, for example, irradiate them with, say, ultraviolet photons from stars that are newly forming, or if there are cosmic rays coming in and hit those ice mantles, then all kinds of reactions can actually proceed, and we can form more complex molecules in those ices. We can keep adding atomic hydrogen in those ices, and we can actually do hydrogen addition in those ices to build up more and more complex molecules. And the reason why eventually we do detect their fingerprint again in the gas phase is because at some point these ice mantles will start to warm up again, and they sublimate. And whatever complex molecules are inside those mantles will get thrown back into the gas phase, into the space between the stars. And that's where we pick up their signal, for example, with the big radio telescopes. And so this is the way how we actually think these complex molecules are forming in space. And let me just finish my talk with a final poll. I think I told you that space is not empty and boring at all, but it's full of complex molecules. But I would like to know from you as an audience, how likely do you actually think that we have life elsewhere in our galaxy? And of course, this is not a right or wrong question, but I'm really curious to see how convinced you are to find somebody else eventually. So let's see. I see 60% of the people voted. And I think, again, we are heavily biased towards the astronomers. We are always optimistic. Okay, so about 80% of the people voted. I don't think the vote is going to change much. So there's a very unanimous vote that most people, actually 100% at the moment, think that there is life elsewhere in our galaxy. And I have to say, I completely second that opinion. I think it would be amazing not to have life elsewhere in our galaxy. And so I think astrochemistry is a very exciting science. And one of the aspects that I really enjoy very much about it is I think it brings us one step closer to understanding our own origins and how the complexity of molecules that eventually form life, such as we know it on Earth, how that comes about even under completely inorganic conditions in space. And so with that, I would like to close this talk, and I'm happy to answer any kind of questions that have come up in the meantime. So thank you very much.
Thank you so much, Inga. Quite an interesting topic. So we'll give a couple of minutes for people to ask questions. And I want to take this opportunity to start the question session.
Yes.
What about looking at extreme environments on Earth? How does that help to sort of look into life elsewhere?
I think it helps us a lot, because by looking at those, say, more extreme conditions of life that we call extremophiles, we can learn how robust life is. For example, I think by looking at life like in Antarctica and also in very hot places in Earth, under the Earth ocean, so very, very deep regions of the Earth oceans, we understand that, for example, places such as moons around giant planets may also be a very promising place to look for life, something that people would maybe otherwise not have considered, because people think like, oh, you know, as life, you have to be on the surface, you have to breathe something. No, I mean, there's life down there in the deep ocean. And so why not have life, for example, on a subsurface ocean of one of the moons? And so I think it has very much broadened our view of how to look for life, and also in which kind of environments to look for life.
Interesting. There's a question on YouTube. Let's go to YouTube first. Do you want to read the question? I thought there's a question on YouTube.
So it's a comment more than question, but Mike says, Stephen Hawking said he thought that there might be very basic and primitive life in about 4 to 5 places in the universe.
Okay. Well, then I would say he's more pessimistic than I am. I think given the vast dimensions, and given especially how little of our own galaxy we have probed so far in looking for life, I would be very surprised if it's only 4 to 5 places.
Right, yeah. There are a couple of questions on Zoom. And before I bring these questions, I'm sorry if I'm not pronouncing everyone's name properly. So Ilya is asking, what are the chemical markers of a civilization that can be potentially observed, except for CO2 and CH4?
Well, I think that's a whole talk by itself. I think it's a very difficult question to really answer, because it's still also part of active research to figure out what is the best way of identifying that. And I think one of the aspects that people are very clear about is looking for a single molecule is not enough, because a lot of the molecules, even if it's, you know, looking for ozone or whatever, a lot of those molecules can be false positives. They can also be made through other processes that do not even involve life in some cases. So I think one of the most interesting, compelling ideas now is to look for an atmosphere which is actually out of equilibrium concerning its chemical composition, because it is actually life on Earth that brings our atmosphere out of chemical equilibrium. And so that could be a very interesting, promising avenue to go.
Right, thank you so much. And Mehran from Germany says, very interesting and fascinating, although a thirsty topic. Thank you so much.
Yes, I completely second that. So since it's the middle of the day, I only have coffee, but I wish you a very nice drink.
All right. Maiko, do you want to bring in the other question from Zoom?
Okay. Because Tilina has some internet connection problem, I will read the question. So another question from Jeremy Frank. Are the same techniques used to identify, oh, I returned on my camera. Okay, so here's a question from Jeremy. Are the same techniques used to identify chemical markers in space used to identify exoplanets for potential atmospheres or compositions?
Mm-hmm. That's a question?
Yeah.
Yes.
Are the same techniques used to identify chemical markers in space which one is used to identify exoplanets for potential atmospheres?
Well, it is looking at the very same molecules partly, but it's not necessarily using the same techniques, because identifying the composition of an atmosphere of an exoplanet is so much more tricky. When I talk about how we find molecules in regions where new stars are forming, we are looking at vast regions of space, and we collect the photons from those huge regions, so we get lots and lots of photons. Now, when you want to detect the atmosphere of an exoplanet and look for the chemical composition in that atmosphere, you have to do a completely different kind of experiment with your telescope, because you have to either wait for the planet to be actually in front of the star, so you see the light of the star transmitting through the atmosphere of the planet, and then see the extra imprint of the planetary atmosphere composition. Or you can also have the planet next to the star, but then you have a huge contrast issue. Your planet is so much fainter than your central star, so you really need to collect enough photons. And then maybe you can play some cross-correlation techniques to actually figure out that tiny little signal from your exoplanet atmosphere. So in that case, you need the fingerprint of your molecule beforehand, and then you play with the fingerprint and find out whether that fingerprint appears in the few photons that you get from your extra solar planet. So it's a different technique, but certainly you are looking for the same molecules.
Yeah, okay. Thank you. Are there any questions? Okay, so it seems, it seems there is no questions for now. So if you have another question after the talk, maybe you can post it on Twitter with the hashtag #SpaceCafeTokyo, then we can find them and answer it if it's possible. Okay, so can you do the announcement?
Let me stop sharing my screen, I
Okay,
think.
thank you. It was very interesting. Actually, I am doing the exoplanet thing, so the contrast is very interesting.
Yes.
Yeah. So, okay, so now we have several announcements for you. So now Atilina has some problem, so can we do that?
Okay, so thank you again, Inga, for the nice talk. Is there any like social media or way to contact you would like to promote? I should ask you that first.
You mean to reach out to me?
Yeah,
no,
if you have more questions.
I'm not on social media. I'm not that person. So you can always reach me by email. You can find my email on the webpage of the university. No problem. I'm happy to answer any emails I get.
Okay, great. So we will tweet that out as well in the follow-up announcement.
That's fine.
Okay, so just a couple final announcements. So our friends over at Tokyo Nerd Night, they've also been having online events the last few months. So they're doing their next event next Friday, June 26th at 8 p.m. So search for them on YouTube and hopefully they'll be back live as well as us. And our next event will be sometime in July. We're still working out the details with the speaker, but please follow us on social media and keep an eye on either Facebook, Twitter, or Meetup. The details will get posted once we finalize the date and the speaker. So thank you again, Inga, and thank you everyone for attending, and hopefully see you next month.
Thanks all for attending. Thanks for the nice questions. Bye.
Thank you. See you.